can be partially and negatively, like parts of an object, even if the whole thing is neutral, parts of it can be negatively charged and the other parts can be positively charged. So maybe even
what's that called?
Polarity?
Yeah, that's the word.
So basically it's a dipole. What's happening is because it's an insulator, the electrons are not going to flow. We're not going to get it so that we have the electrons flowing to one end like if it were a conductor. But if I've got plus minus, I'm not going to do a whole lot of these. I've got a bunch of nuclei which are all positively charged. I got some electrons here. And I've introduced a positively charged source over here.
Oh, yeah.
It's going to attract the electrons. So these electrons that, is buzzing all over the place, that electron's now going to have a tendency to hang out on the other side. So this thing is going to be negatively charged and positively charged. So it should attract to it, and that's the part I was trying to get earlier. And you know what? It's for science.
Oh, no. Let's do it. Whoa. Whoa.
That is hitting my hand. All right. Notice I got attracted towards it, it hit it, and then goes away. That is a better example than what I was doing earlier. So there's a tendency for the electrons to be on one side and the protons to be on the other side of each atom. So we end up with something like this. So because the negative charge is closer, there's a general attraction. This attraction is bigger than this repulsion. So it gets attracted.
But then when it gets close enough, and the positive ions are really close, that's when the repulsion happens?
Yeah.
Oh.
So there might have been some transfer earlier when I dismissed that.
But it's not that, so are the electrons transferred?
Yeah, I mean, this is positively charged. It's possible that these electrons do jump.
Okay. But, so.
And we might not have heard the pop because the electrons, it's not like the electrons are all on one side over here. It's not like they're congregating on one end of it like that did.
Okay. So it's rather like, so it's a combination of those electrons going towards it and the positive, the force of the repulsion getting stronger as it gets closer.
The force of the attraction and repulsion both get stronger as you get closer.
And so, yeah, okay.
So why won't it? Is there a chance that it could stick?
No, because once it sticks, you will have a transfer. You will lose those electrons closest to it, making now you've got positive.
Now you just have positives in there. Okay.
I mean, there's still electrons in there. It's not like you're ripping every electron out of it. If this was strong enough to rip every electron out of that, I think we'd all be dead by now.
But is that possible?
It is possible to rip typically, with a hydrogen atom, for example, you got a nice little proton with an electron going around it, no neutrons if you're doing it right. And you can apply electric fields enough to rip the electron away. And that's how you get protons for high energy experiments.
So you could really make one of those that's just big enough to kill people?
Sorry, I heard.
Yeah,
That's crazy. That can't be legal.
it probably isn't.
Murder usually isn't legal.
And we've got this spring in here. We'll do this one. String one, you just have to pull from the video.
The cartoon. Marcel's probably.
What's going to happen when I turn this on?
That pan will fly a little bit. I don't know.
Why?
May not.
Well, it's touching, so I guess all of the electrons will go to the positively charged ball, and the pan is now going to be positively charged, so that's why it's going to repel.
Yeah. Now, if you're hoping that it's going to hover, just keep hoping. In theory, it could be done, but it won't happen here.
I heard it.
Yeah, I heard that.
Yeah.
So it flew because of the same reason the styrofoam flew? Because of the overcharging of one side, or can I get that again, why it flew off?
Because that is metal, it's a conductor, and so it is pulling the electrons from that onto the positive ball, and then the electrons are getting bled off through the belt and then transferred.
Yeah, where
In
did the
theory, through a ground, but
Like, well, why did that fly off though?
because it starts out neutral. They're both neutral. This becomes positively charged, wanting electrons, and so a source of electrons is the pi pan. So the electrons get pulled from the pi pan into the ball. And so now the pan is positively charged. Those electrons get transferred to the belt, so they're both positively charged, and so they repel.
Okay.
where did the electrons go from the just in the box in the ground in the air?
It should be grounded, and so the electrons are ultimately being led off into the earth. Or the metal box sometimes, because I've shocked myself in the metal box there.
It's not very good grounding then.
No, there's, yeah, it's not. You want to do the hair stand on end?
You can't.
Are you volunteering? You just want to watch it, or you want to volunteer?
Volunteer to do what? I'll do it.
The hand on this and have your hair stand up?
Yeah, I'll do that. Is it gonna shock me?
Better lower
All right.
that.
So if you start with your hand on it, you start with your hand on it, and so there's going to be, the electrons will just flow naturally through you. If you wait to put your hand on it, or you take your hand, actually, at some point you can take your hand off of it while it's going, and it shouldn't hurt.
You're part of the circuit at that point. Don't break the circuit.
Don't break
Yeah.
it.
Let it. It's gonna want to go back to ground, and so it's gonna follow the least path of resistance. It's gonna go back to ground. You're safe.
Yeah, as long as it's.
So I have to keep my hand on the whole time.
Yeah.
This
Don't
video's a
touch
one
anything.
take, right?
Why are we playing?
More dramatic.
For science.
If you're not comfortable doing this, depending upon it looks like you're not using hair products.
No.
Okay, that's good. What you should see is some of the hair sort of coming out of, this is not like Discovery Place or Science Museums where they got the bigger ones and you really see the hair standing out on the ends. It's not like that. But you'll see some of the hair starting to move apart as his head becomes positively charged. And it's pulling electrons from the hairs, and so the ends of the hair are going to be positively charged and should start to separate. You ready?
Sure.
Just to make it more dramatic.
You start to see a little bit of the hair on the fringes there. Shake your head a little bit.
Oh.
Yeah, if you're looking closely, I can see it. I'm close enough to see it, but some of the hair is starting to frizz. You got that lock over here too. is broken.
Yo,
That's the sound of a belt about to break. All right, you should be fine taking your hand off of it.
Sure.
Yeah.
Can't use that thing.
I mean,
It may hurt you.
Yeah, that was good. I hope you saw at least some of that. Again, not a dramatic effect.
no, look, his hair's like.
Look, we see the back is a little,
Yeah,
a
the back.
little fluffy now.
It is? Okay, there you go.
It's like not, like you said, it's not nearly as dramatic as like those big ones in the museum.
Yeah,
But you
oh,
can see
yeah.
it happen.
Those are much better. The one that they actually, the belt that we had when I first got here, it worked much better. The newer belts don't seem to be as effective. All right. I'm sure you're thinking two things. One, this is great, but where's the math?
So where's the
Three things I should say. So where's the math? Also thinking, isn't this about time for a break? And also thinking, wait, isn't there a concept inventory test that you should have given before we did any of this?
Yeah.
And yes to several of those things. So let's take a break. I'll come back with the multiple choice test for this course. It's not for a grade today. And
Not today.
then after we cover the material, you'll do it again. So just take 5.
So we do a concept test every minute.
He does it like that. He'll do
I was
it
like, I was
either-
getting in the shower and like 10, 15, I was like,
Like,
oh, I need to look up with the classes.
Yeah, were you at home?
That'll be
And
actually.
I looked it up and I saw 11, and I was like, I could have sworn this was
Because
11:30.
it's not the same test that we're taking the last one, but it's still, it's just like it's more like an adaptive test of
I
like
didn't even know
how much you learned today
My
versus
gosh,
your
look
last
like
week's class.
Gotcha.
Yeah.
And I think that I
Like a lot.
This
It
is
went
technically
down
the
the
first
whole
physics
length.
class here, so I didn't know what to expect.
Have you taken
So it was
Taiwan
bad there, and I was gonna make it. I was gonna
Oh,
just
yeah.
make it.
Okay.
And I go to turn into Force Tech, and then there's like all these trucks blocking off. I don't know if you saw it. Maybe.
No, I came in the morning.
Saw it. Oh, okay. So they were like working on the road on the left side of Saddles Creek, and I couldn't turn in. So I had to like go, and then everyone else was like funneling to the wrong place. So like everything made me want. Everything was like making me clicks.
Did you watch football yesterday?
Yeah. I also was like getting ready for classes, but yesterday I was so glad that our Cowboys got destroyed. It's like his first NFL pass. The Commanders quarterback they put.
Who did they put in?
I don't. He's a rookie from UNC.
Oh. That was-
He was the good quarterback they had, and now they have another good one.
My friend is a big Seahawks fan. He was watching this game with his family, and we're texting him like in the evening, right? Because
It is Coulomb's constant. Also called the electrostatic constant. In SI units, so in SI, K equals roughly 9 times 10 to the 9th Newton meter squared per Coulomb squared.
meter squared.
8.99 times 10 to the 9th if you want to take it out to 3 significant figures.
What's the C? Where did you say the C was? In the bottom?
That's K is it's approximately equal to 9 times 10 to the 9th.
Newton meter squared. What's the?
Oh, the C, sorry, my hearing.
You're okay.
That's Coulomb, that's C, so the unit of charge. The SI unit of charge is the Coulomb.
Oh, okay. So that's just that's the name of the measurement. Straight
That's
up.
the name of the unit, yes.
Okay. Okay.
And so we can't equate that to anything else we've learned about. It's just like it's a new unit.
It is a new unit.
Gotcha.
Matter of fact, this is a new equation. There are 3 physics equations in the first semester course. I now introduce you to the 4th physics equation.
We're definitely using the other 3, huh?
What are the 3 physics equations of the first semester course?
For force or just in general?
They all happen to deal with force.
1/2 mv squared.
Kinetic energy.
That is actually derived from math and definitions.
But
Isn't it F equals MA?
That's one of them.
Yeah.
Dang
You can't
it,
derive
Chance. You got the one that we don't know how to get.
MVR squared. No, I don't want. What are we there?
Something like I said, MZR squared.
MZR squared.
MVR squared.
Force exerted on like F12 is equal to negative F21.
Oh, that's Newton's third law. Not really an equation, that's just the shorthand for it. I'm going to spoil some of this for you here.
Oh.
Oh, negative.
That looks familiar.
The generalized gravitational equation.
And then
The spring constant one?
Yep.
1/2 K. Oh, negative K.
Yeah. And this is a different K than that K.
force.
Yeah.
That's the K. That's the K he mentioned. Right? No.
It's the spring constant.
That's not.
All right. So, I'm defining these as physics equations and the fact that they basically have to be found, a lot of it experimentally. You can't derive these. Weight is equal to mg can be derived from this. The kinetic energy formula is derived from this. So in this course, there are going to be 2 physics equations, and there's one of them right there. Now it's going to appear like there's a bunch of more equations, but all of those are, at least until we get to chapter 30, they're all basically either math definitions or variations of this, just disguised. This is hidden at the core of it. So let's just do a quick plug and chug.
Oh, could you give us the other unit for Coulomb's constant?
The other, oh, do you have another value?
Yeah.
If you're dealing with, here's the nice unit system, in a sense. If you're not dealing with SI, but dealing with more of the CGS system instead of the MKS system for metric, then K equals 1.
What?
Okay.
And then I guess it would have to be Newton centimeter squared per stat coulomb. Where is this one?
Get asked.
But we're more sophisticated than that. We're not going to be doing this K is equal to 1 stuff.
That's cool.
Just like later on when we do relativity, we're not going to be dealing with this silly speed of light is equal to 1.
Can't do that. So we're measuring Q in C's in coulombs? I mean?
Yes.
Okay.
So the Van de Graaff generator, when we got that fully charged, was going to be on the order of microcoulombs, just to give you some sense. So microcoulomb, 10 to the negative 6 coulombs.
So what is a coulomb?
What is a coulomb?
What is it measuring?
Charge. The coulombs is just the unit for the amount of charge.
So if it's more positive, it'll be a higher coulomb value. If it's
So the charge of an electron, is equal to negative 1.6 times 10 to the negative 19 coulombs. The charge of a proton is positive 1.6 times 10 to the negative 19 coulombs.
Oh. So it's still minusculely small, but if it's positive or negative, that's how you know what the charge is. Because
The way you worded it, I would say no, but I think in terms of,
Sorry.
if I have two negative charges, if I have a -4 Coulomb charge and a -6 Coulomb charge, yeah, it's more positive, but they're still both negative charges. They will repel each other.
Yeah.
We can't, once this is established here, there's no shifting. It's not a relative.
So if what you're signing is your charge. If it's negative,
It's a negative charge.
it's a negative charge.
Yes.
I like that. I
So
like
it's
that a
just,
lot.
it's quantifying how negative or positive it is.
I'll apply that, yeah.
Okay.
Chemistry had me confused.
Yeah.
All right, so let's do a quick plug and chug and read it. I have a 3 microcoulomb charge here. I have a -4 microcoulomb charge there. And let's put 0.05 meters between them.
Okay.
I want to know, what is the force on 3 from the 4? So getting the magnitude is simple enough. It's just you're plugging and chugging 9 times 10 to the 9th times the,
Charges, right?
yep, times the charges. Divided by the distance between them squared. Let's look here. If someone would be kind enough to take that out on a calculator.
Under the F, that's subscript 3 and 4.
Yeah, because I'm calling that 3 and not calling that 4. What is the force on 3 from this one?
Why didn't you put -4? Or you just call
It's just a notation, just so that I keep track of it.
Okay.
Yep, and I did leave.
So we could just call it like 1 and 2 and that'd be
Fine, yeah.
Oh yeah, what's so when you have like the R hat at the end,